Hello, I'm Oded Nir, and I'll be speaking about the joint work with Benny Applebaum, who both from the Tel Aviv University in Israel. And I'll be talking about Advisor-Verifier-Prover games and the hardness of information theoretic cryptography. So first, I'll define roughly what information theoretic cryptography means. So typically, we have parties that communicate with one another according to some predefined pattern of communication. And when we design such protocols, we want to minimize communication in a way that satisfies both correctness, which means that some parties learn new data from the communication, and privacy, which means that some data remains hidden from some of the parties. And the crucial point here is that the parties are unbounded computationally, which makes these protocols information theoretic. And some notable examples are private information retrieval protocols, secret sharing schemes, decomposable randomized encodings, and conditional disclosure of secrets. And due to time constraints, I will only talk about private information retrieval protocols in this talk, though our work has to do with all of these protocols. But private information retrieval will be the running example for this talk. And the thing is, with all of these types of protocols, is that it is really hard to obtain lower bounds on their communication. So today, the situation is that we have exponential gaps between the best upper bounds, which are exponential, and the best lower bounds. And unlike other fields, say circuit theory, we don't even have non-explicit lower bounds on any of these primitives. And unlike NP hardness, NP completeness, we do not have one unified approach that may lead us to lower bounds to many of these problems at once. So our goal in this work is to systematically study the hardness of these primitives. And we will do it through this new notion of AVP games that we will define later in this talk. So I will now begin with defining our running example primitive, the information theoretic private information retrieval. So in this example, we have a client that communicates with a few servers, and the client holds an index to a database held by each of the servers, and the client, that's the correctness property, wishes to learn f of x. Now, in order to do so, the client sends one query to each of the servers. The servers reply each of them with its own response, and then the client needs to somehow compute with these responses the value of f of x. And these servers can be trusted, but the point is that they cannot collude or communicate with one another. Each of them answers separately. And this would be easy, but we have, as in cryptography, the privacy constraint that the servers should learn nothing about the index that the client wants to query. So this means formally that the distribution of each of the queries sent to each of the servers is independent of x. So like all primitives that I mentioned earlier, the communication of peer, we do not know that much about it. We know that the lower bound is linear. If you think about it for a second, the lower bound of exactly n should be trivial from information theoretic reasons. And it took some work to get to even a constant improvement for that. And the best upper bounds, it also took a lot of work, are exponential in the square root of n. And I will say also that from now on in this talk, we will only deal with private information retrieval protocols with a constant number of servers, and when the servers only answer a constant length response for each of the queries sent by the client. And in this regime, actually, this is equivalent to smooth locally decodable codes with a constant number of queries and a constant alphabet size. We'll not mention it during the talk from now on, but if it's more convenient to think of it that way, then it's possible. And as said before, this case of the exponential gap, we have it for all of the primitives. For conditional disclosure of secrets, it's the exact same gap between exponential and square root of n to omega of n. For secret sharing and decomposable randomized encodings, the gap is even larger, between an exponent in n and omega of n squared, roughly. And in this work, we introduce a new interactive proof system that has some kind of online-offline trade-off. And we show that given an hypothesis about this system, that it has to have a lot of communication, we will get super polynomial lower bounds for all of the information theoretic cryptographic primitives mentioned so far. So now I will discuss this new interactive proof system, but I'll first recall what an interactive proof system generally is. So in the most standard case, we have a verifier which is computationally bounded, and it holds some input x, and a prover that cannot be trusted, but is computationally unbounded, that knows if this x belongs to some language L, and it wants to prove to the verifier that it does. And to do so, the verifier and the prover communicate with one another, and after this communication ends, the verifier should either accept and say that x is in the language, or reject and say that it is not. And the standard definitions that there is, we allow for constant correctness and soundness errors. So this is a well-known model, and we modify it in a few ways. So first, now let's introduce the Advisor-Verifier-Prover games. This model will be non-uniform, which means we allow for a different protocol for every input length. Here the input length is denoted by n. And more importantly, we split the role of the verifier to two parts. One of them, we'll think of it as the offline part, and one as the online part. And here the offline part belongs to the advisor. And the advisor takes as an input the entire truth table of the function in question. And it can do whatever it wants with it, and then send one message to the verifier. We'll call that message A, and after it does that and sends this advice to the verifier, it terminates its role in this protocol. And from there on, it's a standard protocol between the verifier and the prover. They communicate with one another. We will limit these protocols to work only in one round, which means the verifier sends one message to the prover, gets one message back. And after this process, it has to decide whether f of x equals 1 or f of x equals 0. The prover would like to persuade the verifier that f of x equals 1. So it probably takes a bit of time to get used to these models and think of all its quirks. So I'll say a few more things. One very important is that all of the parties here, unlike before, are computationally unbounded. This still, let's say, does not help the verifier because it knows only the input, and the advisor doesn't know the input, it knows only the function, so none of them can solve the problem on its own. We would require perfect correctness and constant soundness error. And each advice should only work once for one protocol for proving that f of x equals 1 on one input x, and not for many inputs sequentially. And our goal will be to minimize the total communication in this protocol, the sum of the lengths of all of the messages. And it's easy to see that any function has a protocol with complexity 2 to the n, because the advisor can just send through his advice the entire truth table of f, and then the verifier can just see what f of x is equal to. So 2 to the n is trivial. We wonder, can this be improved? So if we tweak this model in many ways, we get notions that are equivalent to other models, which all have exponential complexity. Like if we remove the prover, if we say the prover is trusted but cannot compute everything it wants, or if the advice should be reusable. But if we allow for multiple rounds of communication between the verifier and the prover, then it turns out then that this is equivalent to non-uniform delegation of computation, presented in the classical work by GKR. And then every function can be solved this way with this kind of game with polynomial complexity. And it also turns out that even if we limit ourselves to one round of communication, if we allow the prover to send long messages in linear size, then we can also get a polynomial communication here for every function. And this leads us to the hypothesis I mentioned earlier, which will be about prover laconic advisor-verifier-prover games, where the prover can only send a constant number of bits. And we hypothesize that in this case, AVPs require super polynomial communication. And then our main theorem is that if we have cryptographic primitives such as private information retrieval with polynomial communication for every function, then we can also get prover laconic AVPs with polynomial communication or complexity for every function. And then with a counterpositive, this means that our hypothesis implies super polynomial lower bounds for private information retrieval protocols, but actually we have corresponding theorems for all of the mentioned primitives. So this will also be true for secret sharing, decomposer randomized encodings, and conditional disclosure of secrets. So next, I will prove this theorem, give a sketch to the proof at least. It's not very hard, and it's not hard even for the other primitives. I think the value of these theorems is that we have one model that can serve as a focal point for all of them together. So let's view it. Our goal is now to take a peer protocol, say for 3 servers, and create with it an AVP protocol with a laconic prover. So I recall that in the peer protocol, the client sends one query to each of the servers, gets one response back from each of them, and then it should be able to decode these responses and compute f of x. And that privacy or secrecy means that the input x should be hidden from the servers. And so the AVP protocol should run as follows. The advisor should pick a server at random and pick an input at random and simulate the client to generate a query for its input and the server. And then, since it knows f, it can also generate a response produced by the same server. And this is the advice the advisor sends to the verifier, and then the advice terminates its role. Then the verifier, seeing this query, it knows that the query, its distribution it was produced through a distribution which is independent of x. So it can compute a tuple of queries which correspond to x, having the query produced by the advisor being one of them. So we can send the prover this tuple of queries where one of them is the one given by the advisor, and they both all correspond to the input x. And then an honest prover should just simulate the servers of the peer protocol and reply to these queries. And then the verifier should accept if the prover's response corresponding to the server the advisor chose is the same as the response sent by the advisor, and if the decoding procedure of the peer protocol outputs 1, which means that f of x should equal 1. And this is it. And correctness should be obvious here. If f of x is 1, then the verifier will be persuaded that f of x is 1. But if it is not, and the prover would like to cheat the verifier, it will have to change at least one of its responses in order for the peer decoding to output 1 instead of 0. And then if the prover changes the response sent by the advisor, the verifier will know about it and say that the prover cheated. And this can happen with probability 1 over k when k is a number of servers. And so we get soundness error, which is bounded by 1 minus 1 over k, which is constant as we wanted. And this proves our theorem that peer with polynomial communication implies prover laconic AVP polynomial complexity, and then we get the lower bounds that are implied by our hypothesis. So we have similar theorems for each of the cryptographic primitives. And now I'll talk about some additional results. So until now, I only mentioned hypothesized the lower bounds for AVP, but the question should be asked, can we prove any unconditional lower bounds on the communication in AVP? And in fact, we can. So if we denote by capital A, capital B, and capital C the length of messages sent in the protocol, and if we say that the prover can only compute functions from some function family G, then we show by counting-based arguments a lower bound that A times the log of the size of the family G must be exponential. And then this can give us a few more specific lower bounds. First, if we plug in G, the family of all functions from B bits to C bits, we get this nice looking bound, but it is not very strong, as every protocol where B is of length n already satisfies this inequality. But this lower bound still is helpful, and it allows us to unify and prove at once a few lower bounds that were proved before in previous papers for each of the specific cryptographic primitives. So for example, if we plug in a family G of multilinear functions, then we reprove lower bound on multilinear pair. And similarly, we can reprove with one framework lower bounds for bound and agree secret sharing and conditional disclosure of secrets. And perhaps even more interestingly, some bounds cannot be unified this way. This means that some lower bounds can only work for one specific domain or primitive and do not work for the other primitives. For example, the strongest lower bound for secret sharing for some family of functions of omega of n squared can be beaten in the AVP domain. We have AVP for this function family of only n to the 3/2. And for the composable and randomized encodings, also we have a similar quantitative lower bound, and the AVPs even perform now quadratically better than the decomposable randomized encodings. And to sum things up, I talked about this new Advisor-Verifier-Prover model, and we showed that the single hypothesis implies now several super polynomial lower bounds for information theoretic crypto, which is something that we did not have before. This, in fact, also induces a new partial order over these primitives, because each one of them, if we transform it to an AVP protocol, we get AVP protocol with a different set of properties, which allows us to think of this partial order between the primitives. And this allows us to unify some existing lower bounds to one framework and also to present new separations. And for future work, it is interesting if we can get a converse theorem. That means, can we take an AVP protocol and produce with it information theoretic primitives? So we have some sort of weak converse theorem in this flavor in the paper. And it will be interesting to scale all of the things we saw down to functions in P or in some other smaller family of functions, and not deal with the entire family of all functions over n bits. And of course, it will be interesting to think of other lower bounds for AVP protocols and prove this hypothesis or prove it conditionally, which will imply lower bounds for many open problems. So thanks for listening.